So how's your homework for last week? Okay. So last week we talked about the rotational matrix and the position vector of the transformation matrix. So today we'll be introducing the position analysis of fluid kinematics. And so this is the term of the last week, the homogeneous transformations multiplied together, then you'll get the whole kinematics. So again, this is the syllabus. So today we will have a homework 2, and there will be 4 group of case study, including the last week we left one. So afterwards, we will have inverse kinematics. Then the time for you to propose your proposal. And we're introducing the velocity and statics. Then will be the written exam. So from the position analysis, the velocity analysis, and the acceleration, or you can call it force analysis. So these are 3 main analysis methods for the robotics. And our exam will basically focus on these 3 topics. So today we'll be introducing the whole kinematics. So as you know, the zero manipulator consists of several links connected in series by various type of joints, typically Robotics or prismatic joints. So this is a robot. So this is a Robotic joint. Then this is a link. And this is the prismatic joint. And this is an open loop robot. And to be a robot, you need to connect to a fixed ground. So one end is attached to the ground, and the other end can freely move in the space. So this kind of manipulator is called zero manipulator, and it's an open loop manipulator. So in contrast, like this one, this will be a closed loop manipulator or a parallel robot. And we also can fix the gripper, like here, or hand. This is called a hand effect. So normally we'll put here the base, and here will be the hand effector. And this is the robot. We want to model it. So as you can see, here will be a reference frame for the base, and here will be a reference frame for the hand effector. And the Q1, Q2, Q3, Q4, and Qn. This is the joint angle or the displacement for the prismatic joint. And through the homogeneous transformation matrix, then we can describe the pose of a frame as a reference frame. So the pose includes the position and orientation. So this is a typical zero robot. It's called a score bot. And you can see here the base, and here will be the first regular joint, and this is the link 1. And we have the joint 2, the regular joint, and here is the link 2, and the joint 3, and link 3, and joint 4, and link 4, and so on. And the last one will be the impact. So for the position analysis problems, we want to know where is the position and where is the orientation of the any factor relatively to the phase frame. So there will be two kinds of problems. The first one will be the forward kinematics, and the second one will be inverse kinematics. So forward kinematics is the joint variable are given, and the problem is to find the pose of the any factor. And for the inverse, will be reverse. So we'll give the pose of the any factor, and you want to find the joint variables. So there might be several solutions in the inverse kinematics. So you can see it. So these are the joint, and this is the any factor. So in the joint space, we have two. So all these are the angles or the displacement of the prismatic joint. So in the joint space, we have joint position, velocity, or torque of the joint. Then through the forward kinematics, then we can get the any factors configuration velocity of which in the Cartesian space. And this can express in R. So R is include the position and the orientation. And in the reverse direction, we have the inverse kinematics. And from the pose and from the pose configuration, then we can calculate back to the joint angles. So the structure of the forward kinematic function is like this, and it depends how you choose the R you like. And we have two methods to calculate this function. So the first one is the geometric, or you can call by inspection, and we'll try it in the next page. And the second one will be the systematic way to find this formula, this function, is we need to assign the frames that, like last week, we did. So I think your homework, you have already tried to assign the frames attached to the robot links and use the homogeneous transformation matrices to calculate the forward kinematic function. So let's try for the first one, how to calculate the position of P. I think this is a very basic problem. You can try it. So the input is Q1, Q2, and you also have the length of the link 1 and link 2. So how to calculate this position P? And the output will be Px, Py, and theta. You can try it. So I think through the basic trigonometry, you can calculate the products. So I think the link 1 is really simple. So what the definition of this? What is the angle? It will be Q. So I think all of you can get this one. And how to calculate the link 2? So we will have this one, is Q2. And what is Q2 for from the horizontal, the x-axis? Is Q So for the P, so I think most of you have done it right. So we can just by inspection and we can get the position of the P and the angle of the thing. So this is by inspection or by geometric method. It is one of the methods that you can calculate the A factor of the robot. But if the geometry of the robot is very complicated, then the inspection may be very difficult for you to do the calculations. So that's why we want to have a systematic method to calculate, to solve this problem. So this is the Dynamic and Hollywood frame. So Dynamic and Hollywood is two scientists. They introduced this method in 1955. So I think it's around 70 years ago. And we continue to use this method to for robot frame and robot modeling. So the first rule of the Dynamic and Hollywood frame is the z-axis must be the axis of rotation for the revolute joint, or the direction of motion for a prismatic joint. And for the first one, I think most of you have we have already taught last week. So for a revolute joint, then the axis of direction need to be is the axis of rotation. And for the prismatic joint, then it must be the direction of motion. So the second rule will be x-axis must be perpendicular both to its own z-axis and the z-axis of the frame before it. So this is the second one. So I think last week some of you have asked how to formulate the coordinate systems. So these are the basic rules for the DH method. And through the rules, we can have a very fast method to calculate the transformation metrics. And the third one is all the frames must follow the right-hand rules, and this is calculating the y-axis directions. So you have the z and you have x. So through the right-hand rules, you can have the y-axis. And the fourth one will be optional. So some of you find some of the coding frames in the website or in other papers. They have shifted to different positions. So this is why they shifted. So each axis must intersect the z-axis of the frame before it. And these are three very basic to if you're building robots, and you can try to follow the 4 guidelines and how you form the coordinate system of each robot. So you can try 3 examples. So the first rule is the z-axis need to be in the axis of rotation. So we will have z0, here will be 1. And the second one will be the x-axis must be perpendicular to both its own z-axis and the z-axis of gravivoids. So since this is the first z-axis, so we can just take x0 as here. If you want to do here, it's fine. And the second one, this is perpendicular. So here is okay, but we just follow it. And through the right-hand rules, we all know the y-axis is into the volt. So I think all of you have done the coding right. And the second one, so if we set up the z0 as here, and z1 is about the volt. And we need to pass through the both axes, as the axis is in this direction, z0 is in this direction. So this in this direction we can pass through the both z1 and z0. And we cannot choose this direction, because in this direction the x-axis won't pass through the z-axis. So here will be x1, and through the right-hand rules, we will know the y. So we know this is the axis of rotation, and this is the axis of the motion. And we can follow. This is x0. And but if you come to here, you'll find out that your x-axis, we can choose like either into a volt or we can only choose the into volt, because we have direction upward and direction forward over the axis. And this is the x1. And through the right-hand rules, we can have here. But if you come to the fourth one, the fourth rule, you will find out that your x-axis cannot pass through the z-axis, since the z-axis is here and x-axis is here. So your x-axis cannot pass through z0, and And how do we solve it? This step is optional. Some of the method will do this step and some will not, but this depends on you. So you can just transform this coordinate system into back to here. So here will be z1 and x1 and y1. So you can transform this back to here. So it's still satisfying that the x1 axis pass through the z1 and z0. So do you have any questions about this one? Any questions? So when you're setting up the coordinate system, you can just follow the first 3 steps, and the fourth one is optional. Because some of the robots, if you don't shift the coordinate system, you will have some mistake or problem with it. So it's better if you can shift it. But the rule of the Daniel method is number 3. So the fourth one will be optional. So this is how we number the link and the joint. So the base will be the link 0, and this one is a joint 1. Then after joint 1 will be link 1. Then joint 2. Then after joint 2 will be link 2. Then we can have a joint I minus 1. Then link I. Then joint I. Then I think this one will be the link I minus 1. So I think here I will miss that. And this is the rebel joint, and this is the prismatic. So you can follow the number. So this is the link, and this is the link I, and we have 2 S's in a link. So here we can say it's joint I, and here is joint I plus 1. And remember, the x6 pass through the joint I is zi minus 1, and the z-axis pass through the joint I plus 1 is zi. So I think it may have some many parameters here. So we have basically 4 parameters for the DH parameters method. So we have di. So di is the xi minus 1, the offset, and this is the angular from the xi minus 1 to xi. And we have ai, so it's the joint axis offset to the second one. And this is alpha I will be the angular offset, angular displacement of the joint axis and the joint I plus 1 axis. So this is rotated about the axis. And we will explain it afterwards in detail. So if you see this is the joint axis, this one, the joint I, and joint I plus 1. So AI is the offset distance between the 2 adjacent joint axes. So this is the z axis, and this is also the z axis. So by shifting here the z axis over here, and this offset distance is AI. And if you rotate about the z axis, then you need to rotate the alpha I angle. So is this okay? So basically, it's like this is v minus 1, I minus 1 axis, and this is vi axis. So these two axes are perpendicular to this line, and if we observe this axis over here, and this distance. So we offset this vi minus 1 to here. So this distance will be ai. And this line is the x-axis. It's x-axis. And if you rotate about the x-axis in this direction, then you can get this is the alpha. So Zi is landing will be the so AI is the offset distance along the x-axis. So this is x-axis. So AI is along the x-axis. And alpha I and the alpha I is the trace angle above the x-axis. So the main thing you need to remember is this axis. So that's how you calculate the distance and the rotation angle. So are you clear about the A and alpha, the definition of A and alpha? And we move to the D and theta. So the translational distance D is the two link, the distance between two links, and this is the z-axis direction. If you can imagine that we have two links. Together, these are two links, so this is a regular joint. So this is the joint axis. So these are two links. So this is the joint axis, the link axis, and this is the link axis number 2. And here will be a joint axis. So the distance between these two joints, link axis is D. And the angle will be theta. So D is so it's different from the A and alpha. So D and theta is about the Z I minus 1 axis, and also the rotation about the Z I minus 1 axis. So these are different. And we will have some exercise after that, afterwards to help you to master this knowledge. And if you are in the prismatic joint, then the D will be the variable. And if you are in the regular joint, then theta will be the variable.
So the left side and this side, the theta direction is all clockwise. Is it completely?
So it really depends on your the direction of your rotational axis. So if you are pointing upwards, then this is the positive direction. Then if you're pointing downwards, then this will be your positive directions. So basically, how you make, so because I have already assigned the direction up here, so I can say this positive is this direction. But if you didn't assign your direction, then you need, so then which direction will be positive is depends on the direction how you assign it. So this is why you have like here is the x-axis and that side is the x minus z minus I minus 1 axis. So it's because that, so the link I minus 1, this link, is moved by the joint I minus 1. So this joint will move this link. And however, so the reference frame of the I minus 1 is here. So if you, and the reference frame of I is here. So the reference of I is attached to the I. So it's here. So this is why you need to have one I minus 1 and another one will be the I. So this is the direction of xi. So when you first encounter this parameters definitions, you can just take out the definitions and your configurations And you can just, according to the definition, then you define what is the D and theta and alpha, A and alpha. So any problem with this each parameters definitions? So you need some practice before you can really know how to calculate that. So in summary, so except for the base and the n factor link, coordinate system I is attached to link I according to the following rules. So the z-axis is aligned with the I-1 joint axis. The positive direction of the rotation or translation can be chosen arbitrarily, so it's up to you. You can choose which direction of your axis which is the direction of your rotational or translation axis. So that will determine the positive directions. The x-axis is defined along the common normal between the I and I plus 1 joint axis and point from the I to the I joint axis. So it seems complicated, but the common normal between the two joint axes is a link. So this is the common normal will be the x-axis. And the y-axis is determined by the y-zero. And this is the formal definition of the DH parameters. And if you have seen the last few pages, that one will be more like convenient for learning. So for the joint, AI, alpha I, and DI are constants, and theta is variable. For prismatic joints, AI, alpha I, and theta are constants, and DI is variable. So unit vector Zi along axis of joint I plus 1, and unit vector Xi along the common normal between joint I and joint I plus 1. So the common normal of these two joints is the link axis, is Xi. And these are the four definitions of A, alpha, E, and theta. And we have I think a 3 minutes video to demonstrate this one. So if you have problems about the DH parameters, you can come to me during the break, or you can just watch the video again. And basically, you just follow the rules, then you can get your parameters. And now we are coming to how open the homogeneous transformation matrix. So the first one is D. So if you have two links, then you can have a 4 times 4 transformation matrix can be established. So if you see that from the I minus 1 is this point, and to the H minus 1, so this is the translation distance along the z-axis. So you can see this one is the z I minus 1 axis. So from here to here, this point to here, this distance is di along the z-axis. So we can write it. Okay, I think I forgot one here, so I'll change it. So this is x, y, z, and so we have d1 here for the homogeneous transformation matrix. Any problem with that? I think most of you are already familiar with this. So this 3 times 3 is the rotational matrix, and here will be a position vector. So since that we have a di translation along the z-axis, so our position vector is 0, 0, and d1. So this is for, and this is, if you see here, this is along the z-axis, and we have d for this person. And the next one, we come to the theta. So the theta is defined as, you see this is the xi minus 1 axis, and we transform it here. So the angle between the xi minus 1 to xi about the z-axis, the z I minus 1 axis, is theta. So we just follow it. So the definition of theta is the angle between xi minus 1 and xi about the I minus 1. So just follow the definition. You can find this angle is I. So again, because it rotates about the z-axis, and I think last week we have introduced the rotational matrix of the z-axis. So we just plug in the theta I, and you'll get this. This is rotation about the z-axis, and the position vector is 0, and you form this transformation matrix. And now we come to A. So the definition of A is this one, and we want to move the z I minus 1 axis to this point. So just now in the last one, we moved the x I minus 1 axis to here, and now we move the z I minus 1 axis to the I. So the translation distance, the offset distance along the xi is ai. So again, so you can just follow the definition. A is equal to zi minus 1 the distance between zi minus 1 and zi along the xi. So you can get ai. And as it is along the x-axis, so we will have a position vector ai 0, 0. And we have identical matrix here for the rotation, since the orientation didn't change. So for the last one, alpha. So again, we move it here. Then already the position vector is already the same, but the orientation is different. So we need to rotate about xi to become the same collinear with the zi. So it rotates about x-axis. So you can see this is the direction of x-axis and this is the direction of rotation. So this is alpha I. So you can take it here and rotate about the x-axis and become the I. So again, with the rotation of the x-axis, we have this is the rotational matrix, and we don't have any position vector, and we can get the transformation matrix as this one. So in total, because in the journal paper of the Daniel and Hausenberg, they expressed it as A, so we use A as example here, but if you want to use H or T, it's all okay. If you want to use other symbols. So for the I minus 1 to I, so this is the I joint respect to I minus 1 frame. You just time it from the T Z, T Z theta, and T X A, and T X alpha together. And this will form this. You just multiply the last all matrices together. And this is the Daniel and Hausenberg transformation matrix. So this is the general solution for two joints. So we have break. So if you want to try it, you can complete it by yourself, or you can come up with an question about the EH parameters. So I think some of you have some question about the EH parameters. So basically, this B and theta is the parameter for this joint I. So you can see this one is Bi and theta I. It's all describe the translation and rotation of this joint, and A and alpha are parameters to describe the link I, this link. So this one is in the direction of the axis, and alpha and A is in the direction of x axis. So in the last class, we have already get our general matrix for the transformation matrix. So this is called the DH transformation matrix. So if you have these four parameters, you just put it into this matrix, then it will give you the transformation matrix of these two links. And we can see this is the base, and if we set the frame here is the origin or the 0, and this is the frame of n factor. And for the robot, it's just multiply all the transformation matrix together, and then the Q is the input angle or in the input the translation distance of the prismatic joint. So here, this is the description of the internal of the robot. And also, this transformation matrix is also can describe the external of the robot. So I don't know whether you remember the last week, we have the 10-guy calibration. So here we have the transformation matrix inside the robot, and outside we have the camera and the tools and the calibration board, and this is the global frame. So these are two methods. The first one, you can just simply multiply all the transformations together. So this is from the B to O, and this is to N to E. So together, we can find the n factor coordinate system respect to the base frame. And also, if you can use the geometry method, you can also do it and form your formula like we just now do. But I think in the 3D space, it's very hard to use the geometry method. And that's a very quick example. You can just try it out. And we already give you all the frames, so I think this is very easy for you. I think of you know the z-axis pointing outward for the 3 regular joint. And again, we do not need to use this configuration as our 0 configurations. So first we can change it. So this is just one of the configuration of these robots, you can just change it into a better way to follow these robots. So the zero configuration of the robot you can set by yourself. So I think this will be easier for you to generate 4 parameters. So we will first do with the D and theta. So as you can see, there is no rotation about the z-axis. So only this is the input. And if you want to translate along the z-axis is this direction, so I think there is no offset in this direction. So the D0, the D1 is 0. And for the A1, this is the offset distance between the this Y Z Z0 to Z1 and another X1 direction. So it's A1. And we can check whether there is offset rotation about the Z0 and Z1 along the X1. I think there is no rotation, so it's 0. And after you get this, I think it's all the same. So you get the DH parameter for this robots. So it's this one. And you just like going to a general form, then you can get from this, you can get the transformation matrix of 0 to A. So I also know how to revert it. So fine. So this is a general form of the EH transformation matrix. So you don't need to remember this. We'll give you the exam. And so like for abbreviations, so like cosine theta I is equal. This is equal to cosine theta I for the short form. And you also can write it like this: Ci is also equal to cosine theta I. And usually, if you want to like have like theta 1 minus plus theta 2 and plus theta 3, so you can write it as theta 1 3. But this short form you need to indicate in your papers or in your exam papers. You need to indicate this, how you shorten the form, or how you abbreviate these functions. So all these are acceptable. And if we plug in this one, the cosine theta 1 and sine theta 1, and for alpha, alpha is 0, so cosine is 1. So we have sine minus sine theta 1 and cosine theta 1, and alpha is 0. And this one is sine alpha is 0, so 0, 0, and cosine alpha 1 is 1. And this is A1 cosine theta 1 and A1 sine theta 1. And the D is 0 here. So you can see it's equal to the transformation matrix for A 0 to 1. So if you have these parameters correct, then you can just very fast generate all the transformation matrices for the robot. You don't need to calculate like your homework each frame by each frame. And this is the Star robot. You can see how it's do the manipulations. So basically, it has 2 rotations, and this one is the 3rd rotation, and also a translation. So this is the 4th degree of freedom robot. So this Star robot has used a lot in our industrial purpose. So generally, you can go X and Y and Z, and also the theta in the rotation. So it is 4 degree of freedom robot. So now you can formulate your coordinate system for Star robot. So this is the rotation joint, prismatic joint, and the rotation joint. So you can formulate your coordinate system according to this. You can give it a try. First, you need to set up your coordinate frame. And how you set up a coordinate frame, you need to follow the 3 or 4 rules we just introduced. So as you see, our base frame basically is here, and our egg factor frame will be here. So since we have 4 group afterwards, then we'll do it faster. So you see, here is the base frame. So if this is the rotation of the direction, so z0, and depends on you whether you want to set your x here or x here is fine. And we can see for the next one, this is the x1 and z1. So x1 pass through the z1 and z0, and also it's perpendicular to these both axes. And the next one, because the motion is downwards, so if you want to set upward, it's fine. But here we set the z2 as downwards, so z2, and also we follow the x2, so the x also pass through both the axes. And for the last one, then the rotation is here, so we also set downwards. And so we have, and we just copy the x3 and x4. And this one is also just like move the reference frame 3 to here, and we get all the written frame. So this is our DH parameters. And because our y-axis is this direction, if you follow our general, if x-axis is in this direction, then we don't need this 90 degrees over the data. So we can see from here to here, this is the translation along the z0 axis. So it's d1, and from these two, because we have 90 degrees, so we have a theta 1 plus 90. This is 90 degree will be in the theta 1 degree. And also because this rotates, so we have variables. And from this joint, the z0 to z1 along the x1, so it's a1. So we have the parameters for this form, and I think the others are the same. So from this one is the theta, the z, and this z is in collinear, so we don't have any shifting. And this x and here this x is also, so theta is don't have any constant variables, only have the variables. And things that this Z1 and this Z2 is 180 degrees above Z2. So we have pi over here for alpha. And this Z1 and this Z2, the offset distance is A2. So we have the A2 for the A parameters. And all these are just copied. And we have a displacement. So the displacement is along the Z2 axis, so it's D3. And it's along the Z3 axis, so it's D4. And we also have, this is the real joint, so we have this as well. And we already bought all the variables, so these two are constants, and this is constant also. And through this, and we can have all the homogeneous transformation matrix, just like going to the general form. So if you see this general form, so you can see here we have four variables, T1, T2, and T3, and T4, and we set this like D1 is equal to 100, and D4 is equal to 50, and A1 equal to 100, and D2 equal to 200. And we just key in all the homogeneous matrix. This is A01, A12, A23, and A34. Just like the program did. Then we just times multiply all the homogeneous transform matrix together. Then we can get our transformation matrix for the N factor. So this is the solution of this forward kinematics. Since the symbol is much more complicated, we can just plug in the degree. So for T1 is 0, T2 equal to 0, and T3 equal to 0, and T4 equal to 0. So this is at the 0 configuration. So let's see what is the answer. So we can see here is the x-axis is equal to y-axis of the basic frame, and the y-axis is equal to x-axis of the basic frame, and z have a minus, and it's 400 in y direction and 50 in z directions. Then we can compare with our settings. So in the N factor configuration, y-axis is same as our x-axis, and x-axis is same as our y-axis, and z is just a minus, so it's reverse. And let's see if we have 200 and 200 is 400, and this is 100, and this one is 50, so the height is 50. So we have our model correct. So if you want to check, verify, you just plug in different number and check whether you have the answer. And we'll quickly go through the scoreboard since we have lack of time. So this is the scoreboard. I think we have the photo previously in our previous slide. And this is how we set up the coordinate systems. So Ideally, this will not be our zero configuration. You can just, if you want to go straight up or you want to go in horizontal, it's up to you. So how to set up a zero configuration is by yourself. So everyone's zero configuration is different. It's how you set up the zero configurations. But some of the configuration may be easier to formulate your gauge parameters. And also, this is a Puma 560 robots. And this is a coordinate system they set up online, but it didn't follow the both rules. As you can see, the Z1 is up here and Z2 here, but the X didn't touch both the axis, but it's still fine. So the number 4 rule will be optional. And this model is also in our toolbox for robotics for Meta by Professor Peter Koch. If you are interested, I think last week we have already showed you. So it's the model, this one. So if you install this toolbox, then you can play with the so this is P560 is the model number, and FKIN is stand for the forward kinematics, and QZ is the zero configuration. As you can see, it's all zero angles. Then it shows you the transformation matrix. This is the rotation, and this is the position of this robot. And it also has a simulation. So it's P560.teach. So then you can have the robot, and you can play with all the angles. They have all the simulations, the 6 joints. And this simulator, this toolbox also, you can build your model by using this toolbox. And it also can generate your simulation if you want to try it for your own modeling. Then this is for today's forward kinematics, and I think we have the first group for this study. If you have any problem, you can come to me during the break. Good afternoon, everyone. Today I'm talking about medical robots, the field, the revolution, the way we think about healthcare, the rapid advancement in technology. Robots are no longer a future concept, but an integral part of modern machine. And what is the medical robots single boot? It refers to the application of robot system in healthcare. These robots are designed to assist doctor and nurse in a variety of tests, ranging from performing complex surgical to helping patients recover from injuries. Medical robots combine
cutting-edge technology like visual intelligence, machine learning, and sensor systems. Now, I'd like to explore some of the key features of physical robots. Many robots are specialized robots designed to assist nurses in delivering patient care. This is a key function. Patient mobility assistant can help patients move from bed to the wheelchairs. And two is in medication delivery. Those robots can deliver medication of support. And three is the vital signs. Can monitor patient vital signs by heart rate, blood pressures, and oxygen levels, transmitting data to nurse in real time. And four is the hygiene assistant. Some nursing robot assistant with the basic pregnancy testing, including pregnant or changing mesh. Number five is the communication support. Attention to communication with nurse or doctor remotely. This is emotional and social support. Engage with the patient, reduce feeling of loneliness. This is a rehabilitation robot. The robot is another groundbreaking robot such escalators are used to assist patients who are recovering from spinal cord injuries. This device helps patients regain mobility by guiding their limbs through specific movement. It is a surgical robot, arguably one of the most well-known areas. Robot systems like this WNC surgical system are used by surgeons to perform minimally invasive procedures. Such robots are advanced robot science used to assist surgeons in performing complex procedures with intense precision and change implant. About structure, first let's talk about MOSI. MOSI's structure is based on a well-built platform, providing stability and flexibility in hospital environment. Similar to an AMR, MOSI is equipped with a 7-axis robotic arm, capable of lifting and handling objects at various heights and angles. It is also fitted with a depth camera that can identify and handle
medications or medical supplies. Most optical radar technology enable it to avoid obstacles in crowded hospital environment. Additionally, it has impact storage compartment, enhancing safety and critically in medical settings, making it an efficient assistant for healthcare staff. Next, let's look at Locomet. Locomet is a robotic assisted game training device, primarily used for rehabilitation therapy. Its structure includes an exoskeleton that supports movement and provides physical support to the patient. This exoskeleton is adjustable to fit patients of different body type and it equipped with multiple actuators to control the hip and the knees. Simulating natural walking movement. Locomotive also has a treadmill system allowing the robot to offer support and guidance during that training. The combination of the exoskeleton and the treadmill creates a dynamic training environment that helps restore walking function in patients with impaired mobility. And the RNC surgical system. The RNC system is a complete multi-component with robotic platform designed for minimally invasive surgery. Its structure includes a surgeon operating console, for robotic arms. Of these, the arms are used to perform surgical tasks such as grasping, cutting, and suturing, while the fourth arm controls the 3D stereoscopic vision system, providing the surgeon with a highly detailed view of the surgical area. Each robotic arm typically has several degrees of freedom, allowing for a wide range of motion. The process execution of delicate surgical procedures. These are make the natural movement of the surgeon's hand, enhancing flexibility and control. The high definition camera delivers real-time high-resolution image, allowing the surgeon to observe the surgical field with extreme precision, which is critical to the success of the procedure. Summary, the structure of these three robots plays a critical role in their practical adaptations. Moses built platform and the robotic arm has been successfully implemented in several hospitals, assisting staff with the efficient transport of medical supplies and reducing their workload. Automated adjustable exoskeletons is widely used in rehabilitation centers, helping strong and minor or injury patients undergo case training, effectively promoting their functional recovery. Currency's multi-jointed robotic arm has demonstrated their precision and flexibility in thousands of minimally invasive surgeries, significantly reducing patients' recovery times and surgical risks. The structural design of each robot not only supports its core functions, but also enhances the overall efficiency and the effectiveness of real-world medical operations. That's all.
So any questions? Okay, so if no question, I'll just have one. So what is the main challenge do you think the medical robotics face?
I think the medical robot may about reduce the doctor or nurse workload, and it can make doctor when it can make doctor have a vision， 就是可以更精准的去手术。
So you can express this like the doctor can do the surgery in more precise way, or just like this and this? And others, or okay, thank you. So we'll have a break right now, and please, the case study group for the following for this week, please come up there to like load your verification files, or just try to set up your computers, and the others can have break.
Good afternoon, everyone. I'm the tutor, and my group member is Nelson Yang. And our topic is working and lecture robots. And this is our outline. Legs robot mimics animal movement, making them perfect for rough terrain when while robots struggle. They are useful for tasks like search or rescue, exploration, and industrial inspection. Example, including Boston Dynamics Spot, a four-legged robot used for inspection and safety missions, able to handle stairs and rough terrain. Contact Elevate is a concept robot with legs designed for climbing over obstacles in rescue operations. And NY is built for industrial tests, such as inspection oil and gas facility, adapting its gas to different terrains. Lastly is Atlas and Osmo, are capable of running, jumping, and performing complex maneuvers like backflips. And we choose Boston Dynamics Spot to perform structural analysis. First, we can see that spot ingress protection is IP54, and its operating temperature is -20 to 45 degrees Celsius. Net weight is 32.5 kilograms, and its maximum speed is 1.6 meters per second. And it has 5 pairs of stereo cameras. Next, we will analyze it in the following: actuators, leg structure, gate, and leg control, and the last is sensor. And spot leg material used for the leg consists of polycarbonate blend plastic with an inner layer of foam, making it both durable and lightweight. And then spot leg has a total of 12 degrees of freedom with 3 pair legs. These joints allow for a range of movement, much like a human leg. And we can see the picture in the right-hand side. First one is the HAA joint. These joints control the movement of the leg side to side, allowing the robot to adjust its position horizontally. Then we have the HFE joint, which is responsible for moving the leg forward and backward. And finally is the KFE joint. This joint allows the leg to bend, helping the robot step over obstacles and crouch down if needed. And then is leg control. And to achieve smooth and stable movement, motors are often placed near the robot joint, especially in areas like the hip and knee. This motor controls the robot movement, such as uneven terrain or sudden obstacles. Some advanced leg robots also use hydraulic actuators instead of motors. Hydraulic systems are often more powerful, let the robot to handle heavier load. The coordination between the robot joint and actuators ensure it can move in a way that's both natural and effective. And this is the video for leg control. Okay, and next one is robot actuators, which allow it to move. These actuators are designed for dynamic leg robots. These robots use high-performance actuators, meaning they help the robot sense its own position and adjust movement accordingly. This actuator also has a liquid cooling system, which prevents overheating and ensures smooth performance, especially during intense or prolonged use. And then is the sensors used in sports. In order to navigate their environment and move safely, spots rely on the same sensors. One commonly used sensor is the stereo camera, which helps the robot perceive views and create a 3D maps of its surroundings. And it also can display the real-time thermal image in the controller, like a right-hand side picture. And this allows the robot to detect obstacles in its path and calculate the distance to different objects. Stereo cameras are useful when the robot needs to step over or around obstacles. And another important sensor is LiDAR. LiDAR uses laser to measure distance and create detailed 3D maps, and it looks like the right-hand side picture. This is especially helpful when the robot is navigating in complex or unfamiliar environments. This sensor allows bots to react in real time to change in their environment and adjust their movement accordingly. And the last point is sketch in spots. And we can see the green area is the leg on the ground, and the white area is in the air. And in walking, as these two legs are always on the ground, in field for slow speed on even surface. As speed increases, robots switch to trotting. When two legs move together, balancing speed and stable. For faster movements, they use bonding or groping, the faster gauge with longer aerial phases. And each gauge has specific uses, like walking for rough terrain and groping for fast travel on fast ground, allowing robots to adapt to different environments.
So here I will introduce you the applications for the smart robot. It has several applications such as inspection and monitoring, data collection, hazardous environment operations, research and development, construction, engineering, security, and surveillance. As you can see in the figure, it can autonomously inspect facilities, monitor site health, and identify potential hazards. This capability is crucial in industries like manufacturing, construction, and energy. It also equipped with various sensors. Spark collects data for predictive maintenance and creates digital twins of facilities, helping organizations optimize operations. In the figure, you can see it has the thermal sensors. It has thermal sensors, and it also got several visual sensors. So the Spark can be deployed in environments that are dangerous for humans, such as chemical plants or disaster sites, ensuring safety while performing critical tasks. So there might be some suspicious package on the train or the MRT. So if you have heard of Spark, robot can make sure everyone is safe and it can take off the suspicious packages. There are three types of smart robots for different scenarios. The first one is standard spot, used for general tasks like inspection and monitoring. The second one is spot on, features a robotic arm for complex tasks such as opening doors or entering tools. And the last one is travel variant, customizable with different sensors or equipment based on the application needs. This is the last part, is characteristics. Flexibility and mobility. Smart usually navigates various terrains, improving steps while maintaining stability. Autonomy is operated independently, track itself, transfers and self-rise if it falls. Certainty perception. All sensors provide full situational awareness with 360-degree coverage. The last one is user-friendly interface. It is designed for easy operation with intuitive controls for manual or autonomous use. It's a reader can show you applications. And that's all. That's our presentation. Thanks for your listening. And here is our references. Any questions?
So, any questions? So, I just have a quick questions. So, based on the concept of robotics, how many motors are there in the standard spot?
I think there are 8 motors on the center spot.
So, do you think, because you just have mentioned that there are totally have 12 degree of freedoms, and each leg has 3 degree of freedoms, so do you think, so they are coupled joints? They are 2 joints coupled together?
There's 2 motors in each leg, so it has 8 motors for the whole robot.
So the 2 joints are coupled together, right?
Yes.
Thank you.
Thank you.
So, hello everyone. Is everyone having a good day? My name is Shen Chen, and this is my teammate, Xinchen Lai. Today, we're going to present you this our case study on the telepresence robotics. Before we dive in, we want to describe our outlines today. First, we will explain the definition of the telepresence robot. So you can have understanding better to a concept clearly, then we will break down the structure. After that, we will start share the applications that are using in the current field right now. If we have enough time, we're going to discuss some of our reference and where you can find it. So if you are interested in this telepresence robot, you can find it yourself. Finally, there will be a QA time, so feel free to ask questions. First thing first, I feel a little sick today, so if you find out I'm start mumbling, just tell me, I will fix it right away. So let's get started. Since we already know what is a robot is, let's begin with this question: what is telepresence? Or if you already know tele means remotely, then we only have this question: what is presence? It might become very philosophical when it comes to persons existing, or we can turn around and have it in a realistic way. We find out in the Cambridge dictionary, you can find this defined as the fact of someone or something being in a place. Simple, right? A more simple example will be you guys right here today presenting this class, which makes you can see what teacher says, and can see what teacher writes, and hear what teacher says. Maybe in a cooking course, you can smell what the food smells like, and you can taste the food. You can even feel the food's texture, or even touch the plate to see if it's hot to avoid burning yourself. So combine these five senses, it becomes human's perceptive. With this, with you receiving these informations, perceptions, you think about it a little bit, or you might sometimes don't think about it, directly react to it, and cause an interaction with the environment. Therefore, what if a robot get involved and become the agent of you and the environment remotely? With this concept, what I just said, we were given by a definition, a remotely controlled system that enable an user to have perception of being present in a distance environment. So with this, we can start to analyze the structure. In a general scenario like this, like my flowchart shows, something happens in the distance environment. Some event it happens. A person or an object perform an event. The input device of the robot, it might be a sensor, it might be a camera, it might be a microphone. Capture the event, convert it to the signal, just like sensor did, right? After that signal is processed, the signal has sent back to the main user's end, who can view the information through the media device, right here. So here comes the major difference. Last week, we have a team that presented us the social robots, right? So what's the difference with social robots and the telepresence robots? Is the social robots is the command is determined by the robot itself, but the telepresence robot is commanded by human. So this is the biggest difference. After the main user command to a control system and transmit the data back to the robot starts to actuators, the end effectors, and then interact with the environment, the object, or other users. Therefore, in short, telepresence robot, again, is a remotely system focused on interaction of user and remotely environment in real time. With this recognition, we can start to share the application, and that will be presented by teammate Lai. Thank you.
Hello everyone. Next one, I will talk about the application of telepresence robots. According to our distribution chart, as you guys can see, the three application area for telepresence robots are care assistance and medicine and healthcare and education. In the healthcare sector, telepresence robots are increasingly used to facilitate remote consultation between patient and healthcare provider. This technology allows doctors to interact with patients who cannot visit clinics in person, improving access to medical care and support. Moreover,
provide companionship, monitor their well-being, and enable communication with family members or caregivers. This application helps reducing feeling of isolation and enhances the quality of life for seniors. In education, telepresence robots are employed in therapeutic settings for individuals with autism. They offer a controlled environment of social interactions, helping users practice communication skills and engage in social activities in a less intimidating manner. Using teleoperation technology, human operators can command robotic systems from safe and comfortable locations. These robots are designed to be more robust, making them suitable for harder environments, which adds to their versatility in various applications. Uh, this is in real life scenarios. Third-person robot also assists individuals with disabilities in accomplishing daily tasks they might struggle with, such as serving drinks in a cafe, thereby overcoming mobility challenges. Finally, the concept of third-person robot is explored in movies as well. For example, Surrogates depicts a future in 2035 where humans rely heavily on surrogate systems to perform tasks remotely, allowing them to easily complete high-risk activities. And the other one is real steel. This showcases a world where therapists robot replace human boxer to satisfy the demand for excitement and balance. If you are interested, we encourage you to look up this film, as they provide deeper insight into therapists robots. So our reference is made by these two review papers. The first one, the telepresence in the recent lecture with a focus on robotic platforms, application and challenges. And the second one, the telepresence social robotics towards co-presence, a review. These two give us so many inspiration for this report, and also what we can see is the only left. This cooperate has already given so many design in telepresence robots and already application, and also the German Aerospace Center. They are what we just saw. They were developing the VR combining with telepresence robots to working together to that astronauts they can safely work in the space. So this is our presentation today. Any questions?
So, any questions? So, I don't have two questions. And after you see the research, and what do they deal with the time delay in the tennis robotics?
So it relies on a very reliable network. So the servers of it must be very good. The process unit, they have to be really good for supporting the whole system.
So the second question is that you have said that it needs to combine by humans. So, but if in the future, if
the robot is remotely, but it's commanded by a central computer, will you still consider as a relevant robotics?
Yeah, as I said, the major concept of third-person robot, including presence of human being. So maybe it can control by another system, another computer of its like actions working or something, but it has to involve human's decision. Like what we show here. As you can see, this one is already controlled by the computer. It goes into a virtual environment and directly go to the room that human command. So your question, we still think it has to involve human's command, but the other things control how it works, it can be automatically.
Okay, thank you.
Good afternoon, everyone. My name is Gilbert. And my counter name is Wilson. 各位好. Today's presentation is about collaborative robotics, also known as cobots. I will start by defining what cobots are, analyze their structure, explore various applications, and discuss the challenges they face, as well as their potential future direction. I hope this presentation will help you get a better understanding of the current state of this field and the opportunities it offers. First, we will define what collaborative robots are. Then I will analyze their structure and share some examples of how cobots are applied in different industries. We will also address the challenges encountered in industries application and conclude with a future work. Introduction to cobots. Collaborative robots or cobots are designed to work together alongside humans in shared workspace. They have been widely adopted in manufacturing, logistics, and healthcare industries. With their greater flexibility and adaptability, cobots can significantly enhance production efficiency and enable several human-robot collaboration. This image shows a typical industrial robot arm and is used in various applications, demonstrating its critical role in modern manufacturing. The icon arranged in a circular pattern represents different industry use cases, while the robotic arm in the center highlights its versatility and multifunctional capability as general purpose tool. Look at this packaging and penalties. Cobots can efficiently handle packaging, arranging and stacking products onto pallets. They manage heavy or fragile items with precision and speed, enhancing the packaging process while minimizing manual handling risks. And then analyze. In laboratory settings, robotics arm can ensure the repetitive experimental procedures such as sample distribution and reagent mixing ensure data accuracy and minimize the human error. And machine handling. Machine handling cobots are often used for loading and unloading tasks in automated machine tools and process centers, reduce repetitive manual operations and increasing automation efficiency on production lines and industrial assembly. In assembly lines, robotics arm can perform a variety of tasks such as component assembly and screw fastening that can adapt their operation flexibility to meet production requirements. And pick and place. Robotics arm can quickly and precisely pick up objects from one location and place them in another, making them ideal for electronic assembly and food packaging industries. And quality inspections equipped with vision system. Robotics arm can automate inspection, measurement, and identification tasks, ensuring that products meet quality standards. And screw driving. Robotics arm can be used for autonomous screw driving with precise control, making them suitable for electronic product assembly and auto manufacturing, which significantly improves assembly speed and injection molding. Combs are used to load and unload injection molding machines, trim edge, or perform post-processing tasks, reduce risk for personnel working in high temperature or hazardous environments. And last, cooling, displacing, and welding. Cobots can perform precise cooling, displacing, and even welding operations, improving production efficiency and ensure high quality results. And history of collaborative. Now let's look at the history of collaborative robots. The evolution of cobots can be traced through different stages of industrial revolution. It began with Industry 1.0, which utilized water and steam power, followed by Industry 2.0 with the introduction of electrical power, Industry 3.0, electronic and IT were integrating into production system. Enabling automation, today we are in the era of Industry 4.0, characterized by cyber physical systems and smart manufacturing technology that enable advanced monitoring, analysis, and automation operations. Cobalt structure analysis. Next, let's delve into the structure analysis of collaborative robots. The structure of a cobalt typically includes multiple interconnect joints and links, allow for a high degree of flexibility and precision. These joints can range from simple to X-configured to more complex 7X setups. This slide illustrates different configurations of cobots. And figure 1, page 8 is configured, is designed to have enhanced dexterity, providing more flexibility to operate in confined space. It is commonly used in assembly and material handling. And 6-axis control with 2 parallel axis configuration. This design increases stability and reduces operation complexity, making it ideal for precise movement required in welding and quality inspection. And 6-axis cobalt with 3 parallel axis configuration. This configuration is optimized for tasks that require simulation motor axis movements such as painting or complex assembly. Module joint structure and analysis. Now let's focus on the module joint structure analysis. Collaborative robots often use module joints, which consist of several key components. These include a motor, encoder, drag, torque, sensor, harmonic
reducer, and driver. Let me briefly describe the function of each component. And motor and hollow shaft. The motor is connected to the valve generator of the harmonic reducer and drives the motion of the cobalt joints. And torque sensor. The torque sensor is positioned and the output port of the reducer to provide accurate measure of the applied torque. And brake. The brake is used to lock the hollow shaft and stop the motor, ensuring joint stability when needed. And encoder, the dual encoder step are measure the position of both the motor and the output port, providing precise feedback for better control. Harmonic reducer. The harmonic reducer, known for its high reduction rate and low mass, enables smoother and more compact joint movements. Left driver. The driver controls the motor's movement and transmits data to the central controller, which ensures real-time control and coordination of the entire system. Through this module joint design, operating robots can achieve high precision, flexibility, and better load capacity, making them highly suitable for complex and dynamic testing.
Hello everyone, I'm Wilson, and today I will present an application of cobots in different fields. Let's begin by looking at their application in the assembly and manufacturing. Cobot has fundamentally transformed traditional production models. In the past, automation relies heavily on large industrial robots to perform repeated tasks. These robots often need to be constrained by safety norms and could not interact directly with human workers. In contrast, cobots can work alongside humans, operate in the same workspace, and ensure safety through advanced sensing technology. Moreover, cobots are highly flexible and adaptive, able to quickly respond to change in production requirements and perform a variety of complex tasks. Thus, when production models shift from large-scale standardized production to small batch, the cobot can effectively adapt to this change, demonstrating its potential flexibility and adaptability. Next, let's discuss cobot's application in the material handling and packaging. The focus in this area is on improving the flexibility of handling operations, reducing repeat tasks for workers, and ensuring the efficiency and safety of the entire packaging process. In logistics and warehouse management, cobots equipped with autonomous mobile robots can achieve automated sorting, transportation, and stacking of materials. For example, in e-commerce warehouse, cobot can receive command from warehouse management system and accurately move ordered items from storage area to packaging zone. And cobot also prove their value in quality inspection. In the electronics manufacturing industry, cobots are often deployed at the end of production lines to expand the quality of circuit board welding, using camera and identify the defects. Cobot can automatically classify and sort products based on inspection results. This intelligent operation not only improves the overall yield rate of production, but also significantly reduces their risk of defective products into the market. To better understand this technology, we can watch a video to show the practical application. So this cobot is developed by TechMan Robot, a company from Taiwan. In detect structural defect, the key feature of this robotics arm is built-in camera, which emulates the need for extra camera installations, thereby enhancing their system's integration and operational flexibility. And next, we can show another video for agricultural and farming application. Cobot can be equipped with camera and to access the ripeness of fruit and perform automated harvest using robotics arms to ensure that only fruits at optimal ripeness are picked. And next, we will discuss one of the main challenges faced by cobot: safety. The primary goal of cobot is to ensure the safety of human workers in shared environments. Since cobots are designed to work alongside humans in the same workspace, safety becomes a crucial challenge in their design and application. One of the key safety challenges for cobots is contact avoidance. The core objective of contact avoidance is to prevent potential danger contact, ensuring that operators can work without the risk of interference from the robots. To achieve this, cobot rely on advanced sensing technology and computer vision systems to perceive their environment, and through real-time control strategy and trajectory planning algorithms, predict possible dangerous situations and perform timely avoidance movement. The effective integration of this technology allows cobot to flexible, perceive environment change and respond rapidly. However, relying solely on contact avoidance is not sufficient to ensure safety, leading to another major challenge: contact detection and mitigation. Even with contact avoidance measures in place, unexpected contact may still occur under certain conditions. Therefore, cobot need to be equipped with immediately contact detection and energy mitigation mechanism to minimize the potential harm caused by collisions. In this regard, the robotics arms of cobots are typically equipped with force torque sensor, which can instantly capture collision signal when contact occurs and adjust the robot's behavior through intelligent control algorithms, reducing the energy release during contact with human operators. This design allows the robot to immediately alter its trajectory or reduce its speed upon unexpected collisions, significantly minimizing the impact of risk of injury to the operator. Additionally, Cobalt-based challenge relate to ergonomics, which can be divided into physical ergonomics and cognitive ergonomics. Physical ergonomics aims to align the physical burden on operators. For example, cobalt can perform tasks such as heavy object handling and precision assembling, reduce the muscle and skeletal stress caused by physical labor. However, if the design of the cobalt or the overall production line layout does not adhere to normal principles, it might force operator to work in unnatural position or angle, potentially leading to new health issues. The goal of cognitive ergonomics is to reduce the physical, psychology stress and cognitive load on operators when using cobalt and to enhance users' trust and acceptance. Due to unfamiliarity with the behavior pattern of cobalt and their unpredictable, operators may feel uneasy or nervous when interacting with them. Therefore, future design should be focused on enhancing the predictability and behavior consistency of cobots and providing interface that enable operators to better understand and anticipate the robot behavior. Next, I will conclude today's presentation. This discussion has provided a comprehensive analysis of cobalt technology with particular focus on its application and challenge in the area of safety and ergonomics. To ensure proven safety in dynamic work environments, research have continuously performed various preventive measures such as advancing sensing technology, real-time control strategy, and collision avoidance algorithms to mitigate the risk of accident contact. At the same time, research on economics is gaining more attention, but its real-world application is still relatively limited. More economic study focus on improving operator working posture, reducing cognitive load, and enhancing users' comfort. However, these findings are still largely confined to the laboratory stage, with a significant gap between theory result and practical implementation in real world industry setting. Therefore, one of the key challenges for future research is how to effectively translate this economic theory into practical solutions for industrial application. This is our reference and this is our case study report. Thank you.
So any question for the cobalt? So my main comment is that you have defined that the cobots need to work with a human or work with the human beings, but in your demonstration videos, there is no human present. So the question is that what is the main difference between a general serial robot and a cobot?
We think because we can measure because they can measure the whole environment is safety. Because most of research are doing in the lab, not the real factory. So you need to try to like it needs time to change to test from lab to real factory.
So as you have also shown the figure, so actually the main difference is that the cobots, the joints of the cobots, they need the torque sensors, so they can sense the torque of the environment. So that's how they do the control strategies. And another very good question is that if you know that you need this kind of control strategy like impedance control, this kind of control strategy is this open loop or a closed loop control system. You can just choose one. It's an open loop or a closed loop control system.
We think it is a closed loop because the robot has a torque sensor, so the robot can know what if the robot hits something, he will control itself to don't need a human to control it.
Thank you. So I know it's already end of class, but we still have a homework for this week. So this will be the homework for this week. So we still have 10 points for extra points. So it's just do the explanations. And question 1, 2, 3, 4 is the same. So it's just use the DH method to build up the transformation matrix for the pharma robots. So the first question is to derive the EH parameters, and also you need to show your coordinate systems. And the second one is use the EH parameters to derive the homogeneous transformation matrices for each link. And the third one is to give the forward kinematic equations. And question 4 is if the input joint is 45 degrees like this cube, and what is the position and orientation of the robots? Because like these two questions, maybe you need to use softwares, but if you don't know how to use the MATLAB, or you can just use the Excel. Excel also can calculate the matrices. And all these 4 questions are 100%. And the figure is here. This is for non-robots. And we'll assume the figure B as a 0 configuration of this robot. And if you have any questions? Do you have any questions? So just basically use the DH method to modeling this robot. And you can have the forward kinematics of the robot. So any questions? And if no, then I think it's the end of this lecture. Thank you.